This is the variable connecting rod, a technology that works to change the compression of an internal combustion engine. And here we will analyze its working mechanism. Speaking of compression ratio, it will be directly related to the performance and power generated from an engine. If we increase this compression ratio, the engine will be better, although this condition must also be accompanied by more quality fuel. But on the other hand, in turbocharged engines, the engine compression will be deliberately designed lower, because when the turbo blows air, the cylinder will be filled more, and with more air, the compression of the engine will increase as well. However, when a turbocharged engine is working at a low load, such as when driving at low speed, the turbo of the engine will not work optimally, and the engine will also work with a low compression ratio. This inevitably causes the turbo engine to consume more fuel in this situation. So, how to solve this problem? The only way to overcome this problem is to create a technology that can work by changing the compression ratio following engine conditions. And as a solution comes the variable connecting rod, which is currently being tested on the BMW 240i. In 2013, Professor Dr. Carsten Wittek was the person in charge of the piston engine laboratory at the Hochschule Heilbronn University in Germany. Wittek knew that just as variable ignition timings or variable camshafts were invented in the past and recognized today, variable compression ratio also had great potential to increase the potential of internal combustion engine. Based on this idea, he decided to start his research and develop a connecting rod whose length can be adjusted according to engine conditions. In simple terms, this VCR works by eccentrically rotating the pinhole to raise or lower the piston, so that later it will increase or decrease compression. To make it easier to understand, let's analyze together in detail how it works. First, here we have a normal-looking crankshaft, but if we look inside the crankshaft, we will see two additional modified oil channels. Whereas the original channels are responsible for lubricating the bearings as usual, the additional channels will only work as required by the ECU. This oil will flow to the rod cap through a channel and actuate a valve on the connecting rod. When pressurized, it pushes the valve, and when not, a spring pushes it back. In this way, the oil is sent through the desired channel. Then on the connecting rod, which as you can see will have two internal cylinders. On the wrist pinhole, we will have a moving part with an eccentric hole. This part is named epsilon E. When the epsilon rotates, the off-center hole moves up or down. This epsilon itself is recognized by two mini pistons that move through the connecting rod cylinder, which will be given oil pressure coming from the crankshaft as needed. This oil pressure is intended so that the epsilon can maintain its position when the engine is operating, and this condition applies to both pistons. Which means that the first piston serves to increase compression, and the second piston serves to decrease compression. In the first project, the connecting rod did not have an oil passage, but instead used an additional arm that moved and connected to the connecting rod and was responsible for supplying oil. This mechanism is called Varamot. Obviously, this additional part would give additional weight and workload to the engine, but this was temporary until the double oil crankshaft system was invented. With the epsilon operating and the lever being eccentric, the oil pressure requirement to maintain the piston position was very low. Exactly only 3 bars of oil pressure to maintain the position of the piston, operating at 3,000 revolutions per minute, and to keep the oil pressure stable at low engine RPM. Then this oil pressure will be generated using an independent electric oil pump. Another VCR model works in a very similar way, but this model uses gears inside. The gears are also driven in the same way as before, and when the mini piston is moved by the oil, the rack moves and rotates the epsilon, lowering or raising the piston. However, this system is no longer used and the former system is considered preferable. After years of research and development, in 2016, a BMW 240i F22 with manual transmission was added to the project. The car is equipped with a 3.0-litre six-cylinder engine that produces 340 horsepower and 500 Newton-meters of torque. The compression is 11:1. The 6 connecting rods were replaced, and for the crankshaft, instead of drilling a new oil passage, the use of a mobile actuator in the crankcase section was considered more preferable. On the rod cap, the internal valve has a protruding part that, when it passes the actuator, bumps and operates, eliminating the need for a crankshaft oil passage. The oil pump is modified to always maintain a minimum pressure of 3 bars or 43 psi and is able to operate the mechanism. Its compression ratio can be easily varied between 9.7 and 13:1. The good news is that the car has been tested on a dynamometer, and finally, for 2019, the 240i is hitting the streets. Higher turbo pressure and power can be achieved by lowering the compression from 11 to 9.7. It is also possible for engines with VCR to operate using only lower quality fuel, especially at low speeds, which is 90% of the time the engine is running when we go to work. And it is claimed that the advantage of higher compression results in fuel savings of 5%. In addition to the BMW 240i, the small 3-cylinder engine of the Ford Fiesta EcoBoost was also modified, and laboratory testing was carried out, but with the crankshaft hydraulic system we mentioned at the beginning. Let us now move on to the drawbacks of this engine. First, connecting rods are more complicated and have internal moving parts that can get stuck. The connecting rod construction is weaker than the original due to the complex design and many hollow parts. Its complex shape and hollow parts increase production and assembly costs. The connecting rod is heavier, so it can limit the number of RPMs. An electric oil pump is also needed to keep the pressure stable. On the other hand, this machine also has quite interesting advantages. In the event of a failure in the hydraulic system, the ECU can adjust the turbo and ignition parameters to slightly reduce power and avoid damage. By applying a command system that is directly attached to the crankcase, this technology will be easier to apply to existing vehicles. While the double oil crankshaft system is better for engines that will be produced from scratch. With the right alloy in the connecting rod, coupled with good computer design, a light and strong connecting rod can be obtained, albeit a little more expensive. This system can improve efficiency and result in fuel savings of 5% to 8%. Simply put, the system will pay for itself in additional costs as it is used. The system can operate with any fuel quality. Modifying the engine and installing this system is not too complicated. We only need new connecting rods and actuators on the crankcase to change the position of the connecting rods as well as ECU tuning. And that's it for the cons as well as the pros. Finally, in 2022, research has begun to move into a deeper stage of hydrogen fuel application, with the engine expected to be operational by mid-2024. More information can be found on the university's website. We think the opportunities of this fuel are very wide, especially with the presence of white hydrogen, which was recently discovered in France, which is claimed to be used as a substitute for current fossil fuels. And what do you think? Will the technology be able to compete in the middle of 2024? Or will it require even more research time? We'd love to hear your thoughts in the comments below.